Thank you. Thank you for the invitation to speak. I'm going to talk about sample-starved situation where you have an objective to estimate certain properties of a correlation matrix in a very high-dimensional setting. And I'm going to motivate this by some applications to please David. And then I'm going to jump into some mathematical results and talk about one of the principal ideas that comes out of this type of approach, this type of formulation of the correlation mining problem, which is online multi-stage sampling prediction adaptive regression using correlation screening. So this is work that I've had lots of help with over the years, and these are some of the sponsors and students that have helped me with this. So here are the applications for David.
Thank you. Thank you.
Yeah, so I worked many years on trying to extract relationships, dependency relationships, correlation, nonlinear correlation from different types of high-dimensional data like gene expression, email spam networks, social data, social networks, microscopy where you have images with very high-dimensional features, and different types of problems in tracking. And the objective in all of these has been to construct some sort of graphical model, if you like, that captures the relationships between variables. The problem is that you have lots of variables and you only have relatively few samples in these situations. For example, in looking at coming up with these molecular pathway networks, which are basically thresholded sample correlation or sample partial correlation, you have to form an estimate of the overall correlation matrix, threshold it at some value, or use an optimization approach such as GLASO or some other approach that approaches this from the maximum likelihood framework, and then construct a hopefully reliable network of relationships and codependencies between the variables. So the process of going from data like these 20 sequences, 20 variables with 15 samples each, to the sample correlation matrix, which of course is only going to have a rank 20 here if we have 20 variables, to then a thresholding of that sample correlation matrix where you can extract things like hub degree of the graph as interpreted as, say, this sixth variable here being correlated at some level, say greater than 0.5 in magnitude, with some other variables. And so in this case we have a degree 2 that might be of some significance, either biologically or in other applications like spam networks associated with this, perhaps the person or persons in control of the influence network. And then you can construct graphs like this, where the edges, of course, correspond to non-zero entries in this thresholded sample correlation matrix. The problem here is that, again, we have relatively small number of samples to do inference, to construct these types of graphs, and a very large number of unknowns, right? In the gene expression example, there might be 20 to 30,000 genes in the genome. In the spam example, you might have millions of IP addresses, right? So on the other hand, you only have relatively few samples because they're expensive. So it's a crucial need to manage uncertainty and to look for controlling false positives. And this is what led us early in this work to start to ask questions about how can we characterize reliability of these types of correlation inferences based on observational data like the ones that I was talking about a minute ago, gene expression and spam traffic and so forth. So this is a real problem, and this is a very nice paper that came out of an article in Significance, the magazine of the Journal of the Royal Society of Statistics, in 2011, where they looked at 14 different studies, I should say, And these studies were published in very high-profile journals like Lancet and the Journal of American Medical Association. And each one of these articles basically followed up on those studies, proving that either the claims in those studies based on correlation between variables that were used in the experimental design to come up with, for example, a conclusion that treatment with more vitamin E or beta-carotene will reduce your chance of lung cancer if you're a smoker, were actually specious and did not replicate in a much larger trial. So the problem here is the absence of adequate control of these false positives or spurious correlations. And it's, again, a real problem. So what we did to approach this problem was we looked at the literature, and we found lots of results in the literature on correlation estimation, model selection, and looking at various types of consistency results, sign consistency to recover the right sign of the correlation matrix, and so forth. And all of these methods were based on one or two very limiting assumptions. Of course, if you go far back, 20 or 30 years, it was all based on having a finite and small size of the matrix, that is, few variables, and lots of samples, which is not appropriate to most of the applications that we're dealing with. And then there were another more recent results, which they have the regime where both p and n, p the number of variables, and n are going off to infinity at various rates, but they're both going off to infinity. And so our approach was to say, well, let's see what we can do when n is fixed. So this is a different regime, if you like, that we're exploiting, and we came up with some results on that a few years ago, and I'm going to show you some of those here, and try, if I have enough time, to indicate some of the implications on doing this type of correlation analysis for prediction. So here's just some math to get us going, so that you understand the theorem, and that is that we have some measurement matrix, p by n, that's a typo, where number of variables by number of samples, with columns corresponding to the vector of variables sampled independently and with identical distribution. We assume that the covariance matrix is, of course, now a p by p matrix. It's sparse, row sparse, or block sparse. And of course, that means that the correlation matrix, the normalized covariance matrix, is also sparse. And it has some adjacency matrix A0, which is simply the hard thresholding at any level threshold row of the entries of this sparse correlation matrix. And we can define the support set of connectivity. That's the rows of the adjacency matrix that have more than that have any number of entries. That is from degree 1 to degree up to p minus 1, and the hub degree is, of course, the number of non-zero entries in that corresponding row. And you look, therefore, at the rows that have a hub degree of greater than or equal to delta, and that gives you the delta support set. So we're going to give results for these various discovering these sets with accuracy. So the p by p sample covariance matrix is simply constructed by projecting onto the orthogonal to the one-dimensional space of constant vectors this matrix, and forming the quadratic form of that, you get the p by p sample correlation matrix, which corresponds to an estimate, now a rank deficient estimate, because n is going to be much less than p, of the ensemble or population correlation matrix sigma, and then it of course has its own adjacency matrix if you threshold at some correlation level row, and you can estimate the connectivity support, for example, at that level row. But clearly, we're going to end up with, in practice, some false positives. So we're going to have to carefully choose this row so that we can, in support recovery or correlation screening, as we call it, control either the misclassification errors on the support, in the connectivity support of that is the variables that have some correlation to other variables at that level rho in the sample correlation or partial correlation matrix, inverse of the correlation, or the probability that we get any such variables that have connectivity, given that this covariance matrix is very sparse. The true covariance matrix is very sparse and has no connectivity at level of threshold rho on the population covariance. So if we define n rho as the number of discoveries above the threshold, we end up with false positives because naturally we're in this regime of high sample variability. And so this is what I was saying at the beginning, where there are these regimes of sample rich, where the central limit theorem applies, where we have p is fixed and n is going to infinity. We have the sample critical regime, which fits these semicircle and Marchenko-Pasteur types of results, where you can't estimate with any accuracy the covariance matrix or its spectrum, but you can estimate the maximal eigenvalue, or estimate the distribution, I should say, of the maximal eigenvalue if n and p go to infinity at the same linear related rate. And then the so-called sample-starved regime, where n is fixed and p goes to infinity. So this is the regime that we're really interested in, and it governs this, what we call purely high-dimensional asymptotics. So this is a kind of a new regime because we're letting p go to infinity, n is fixed. Now you might think that there's some voodoo here, because you can't obviously allow p go to infinity and fix n without allowing something else to vary, because you will end up with trivial results where you have all your discoveries are false positives unless you allow some other parameter to vary. And that parameter is effectively this threshold that we're going to apply. And so here's what we do. This shows a simulation of a set of variables. There are 100 of them with a diagonal covariance matrix, so there's no dependency. All positives are false positives in terms of the edge discoveries. It's any value of correlation threshold rho. And so if we have 101, just so barely above the number of variables of observations, we can see that there is a very abrupt increase in the number of false positives as we bring this correlation threshold below this critical threshold, which I call rho c, which is about 0.34. So that means that if you set the threshold below this value, you're going to be overwhelmed with false positives, right? And this is a simulation, so it applies to cases where n and p are finite, obviously, because that's how we've set the problem up. If you reduce the number of observations, this correlation critical threshold increases. It creeps up until you're really between a rock and a hard place here, where there's really no margin for true positives, right? Everything becomes a false positive up here when you only have a tenth of the variables available to do edge discovery or screening. So the region of reliability is within this margin between 1 and the correlation threshold. This critical threshold, given the theory that I'm going to show you on the next slide, can be determined for large p by this expression, which you can see for large n, p to the power minus 1 over n behaves roughly as logarithmic in p, right? So this threshold creeps up very slowly if you have large n. If n is much larger than p, by increasing p, you only get a logarithmic increase in the correlation threshold. So that's the part of the space, if you like, of n and p, where you're in the classical regime, where everything's stable, where increases in p can be accommodated with basically only a logarithmic penalty. Yeah?
Sorry, can you remind me what's Cn again? What is Cn?
Cn is a constant that is related to the underlying distribution of the true correlation, the true covariance, the population covariance. So I haven't defined Cn here.
So you haven't defined
Cn. Yeah, so that's why you don't know what it is. But
that's a good sign. That's a good sign.
Yes, it's hidden in this big O. So if that, so it's related to the packing number of the space and is given by
So Cn depends on the underlying distribution.
It does, except for the case where you have a sparse covariance. So if the number of rows that have degree greater than 0 is of little op, then that Cn becomes independent of the true underlying covariance, and that's key because that allows one to determine false positive rates without knowing the underlying distribution.
So what is Cn for this example where the covariance is identity?
Yeah. So for that particular case, Cn is equal to the incomplete beta function, where the integral from rho to 1 of the complete beta function, so it's completely tabulated and you can determine Cn. Yeah. So this is the theorem, and this goes back to a paper in information theory that we published in 2012. And so it says, and I haven't given all the assumptions here, but if you start out with an assumption that the columns of the matrix X are IID, and each column has a bounded elliptically contoured density with a row sparse covariance. Okay, so row sparse simply means that the degree is of the true correlation graph is fixed and finite, upper bounded, I should say. Right? It's not a regular graph. It's upper bounded, strictly upper bounded, and then you get the following result. If you allow the correlation threshold, which I showed here, to creep up at exactly the rate at which this knee, that is this critical threshold, creeps up, then what you can do is you can maintain, as you increase p, for fixed n, you can maintain the same expected number of, if you want to call them false positives, right? There will be false positives for sufficiently large rho because I've assumed that the distribution is bounded. So there's no perfectly correlated variables, right? So there is some upper bound on the true correlation. So this looks like a limit that should remind those in the audience who are familiar with the Poisson law of how a Poisson random variable, this being the number of false positives of variables that have a degree greater than or equal to delta at a correlation level rho, that the false positive has a probability that behaves in this way, where lambda is the rate of a Poisson function. Is a Poisson variable. It's not Poisson, though, because, I mean, for the case delta equals 1, connectivity is a mutually symmetric relation. So clearly, n cannot be an odd number, right? So it can't be Poisson. But it turns out that this probability behaves like a Poisson variable. Okay, so as I said, this is actually Cn right here. That's the expression for Cn. And we can look at the phase transition threshold that comes right out of this theory as the point at which that knee occurs is measured by the point in rho where the slope is equal to -1. And what you see is that as a function of the number of observations and the minimum detectable correlation, which is the critical threshold, it decreases, and it decreases extremely quickly for a few observations. As you get a very large number of observations, so you're now going into this classical regime, it decreases much more slowly. So what this means is that there's actually a kind of a blessing of dimensionality here, as opposed to a curse of dimensionality, in that just a small increase in the number of observations, if you don't have very much to begin with, can give you a significant decrease in the critical threshold, which means that now you can discover with higher confidence a larger, with high confidence, I should say, a larger region of true correlations.
I think the color code is not showing up.
It's not showing up, unfortunately,
so
here.
Blue
Yeah.
is 1 to many zeros?
Yeah. So blue here is 10 billion, right? See, this is for 10 billion variables. You only need, on the order of about 200 observations to have a critical phase transition threshold of about 0.6. Which is very, very surprising. But of course, in this regime here, you can't discover everything, right? You can't discover all the edges, but you can ensure that the false positive probability of discovering any edge, or of stating that the correlation matrix has some edges, that can be controlled at this level of 0.01, which is this.
Just to get a sense of this point, is high good or bad?
High is bad, right?
High is bad, right?
Because the correlation.
You want a more detectable threshold.
Exactly. So it's bad, of course, as you increase the number of variables.
The better you are.
Yeah, it's the slope, right? It's the slope. So
The slope.
the slope is really, really high down here. So if you have small n, the benefit, the value in increasing the number of samples is larger than it is out here. So in the classical regime, there's not much benefit in increasing the samples by a little bit, whereas in a low-dimensional regime, there is a great advantage, right? And this just shows that. So this shows the a comparison, if you like, between these asymptotic regimes for what we call the screening, which is the theory I've just given you here, the support recovery and the covariance estimation cases, where the error criteria are different, and you can characterize these particular regimes as corresponding to either order 1, the number of observations increases, the complexity, for the sample complexity is basically order 1 in the case of screening, as long as you increase the threshold at that rate, right, so that you maintain a constant number of false positives, as opposed to forcing n to increase at least log p rate if you fix the critical phase threshold at rho star, and then covariance estimation, you have p log p for the sparse case. So we're in this regime where we call it the purely high-dimensional regime, where n is fixed and p goes to infinity, but we control the critical phase transition threshold. So what this suggests is that if you have the ability to collect data in an online fashion, you should do so in a progressive, stage-wise manner. Because take advantage of these regimes. Take advantage of these regimes in screening. You're in this order 1 regime. So you can look at a few samples, say of a very large number of variables. If you're doing, for example, discovery in the properties of the gene expression, you do assays with the full genome, but a few observations. Do screening then until you can be reliably sure that n is large enough with that critical phase transition threshold that you have biologically significant edges, say at rho equals 0.5, and then use downsampling of the variables to focus in on those that pass the screen to do support recovery, and then follow that by estimation as the sample size increases. So it's progressive correlation mining makes sense because you're making use of this table of progressively harder and harder tasks requiring more and more samples in order to do that. So I'm not going to have time to go into these results here, other than say this Sparks procedure does 2 stages. It does screening at 1 stage, reduces the number of variables according to the guarantees, the false positive family-wise error guarantees, to select or pre-screen a small set of variables, and then perform ordinary least squares on those variables. This is similar to Fan and Love's sure independence screening, except here we will do the correlation screening directly on the regression coefficients as opposed to on the unnormalized marginal correlations. So we have some guarantees and some proof of convergence and sample complexity, and showing that we improve significantly over the sure independence screening and lasso in this progressive type of correlation mining task of, in this case, predicting a response variable, and then some real data that's that I don't have time to talk about, where the response variable that we're trying to predict is a symptom. It's a phenotype of a population given a set of gene chip measurements, Affymetrix gene chip measurements. So in conclusion, I hope that I've gotten the idea across that we're looking at this purely high-dimensional setting, which is different from what the very high-dimensional or ultra-high-dimensional or other types of high-dimensional settings are, where n and p are allowed to go into infinity, that we have universal phase transition thresholds that apply to this case of n fixed while p goes to infinity, and that these phase transitions can be very useful for doing this sort of multi-stage sizing, right sizing of the sample as you progressively go through down-selecting the variables to assay. There's a lot of things I haven't covered here. We've done a lot of work in structured covariance, in generalizing this to nonlinear correlation mining, and spectral correlation mining, where you have random processes that you're trying to find the coherency function or coherency matrix using similar types of correlation screening types of approaches. And then I'll leave you just with some references that if you're interested in following up on, you can take a look at. Thank you.
I have a question. So I want to understand better how universal this method is correlation mining. For example, if I don't know your model exactly,
Right.
How can I compute this exact, this critical threshold, things like that? Or if I know the model slightly wrong or very wrong, will that significantly impact?
Good question. So the only assumption here is that we have this elliptically contoured density with a bounded density and this sparsity constraint. So if you're guaranteed that the correlation matrix or the dispersion matrix in your elliptically contoured density is sparse, it doesn't matter what the entries are in the component, the active variables, right? So it's very robust in that sense to the values of the correlations within the sparse correlation matrix. It's of course not robust if you don't have a sparse correlation matrix, then these results will no longer apply.
Do you need to know the level of sparsity? Or
Right, so you don't. It turns out that under these regimes, all you have to guarantee is that it be small order of p. So there's no need to know what the sparsity levels are. Yeah. Of course, there's a constant out in front, which also depends on the sparsity, and that's so if we can't guarantee for p small, but for p very large, that constant basically becomes independent of the structure of the correlation. Yeah. Thank you for the question. It's a good one.
Thank you.